Everybody, welcome to our podcast, Innovating the Industrial World. This is episode 11. I'm John King, your host and CEO of Cross Company, and I'm here with my good friend James Hutchins. We're going to talk today about moving things electromechanically. What does it mean by that? So last episode, you may remember we talked about moving things using air, pneumatics, in really funky environments, and that's why we had to use air and different materials to do that. Now we're going to be talking about moving things very, very, very precisely. And so we're going to talk to James about that. Pretty cool stuff. So James, why don't you introduce yourself to the listeners?
Hi, I'm James Hutchins, and I'm an applications engineer with Cross Company. I started my career in 1999 and as an apps engineer for Cross. Then I moved on and worked at a manufacturer for about 10 years and came back to Cross about 8 years ago. One of the reasons I chose the motion control industry out of college is I liked that it was a dynamic and ever-evolving industry. I liked being able to move things precisely under control.
So this is going to be kind of funny because James is like our hero about moving stuff. Literally, you don't even imagine how much it matters to move things with incredible precision and accuracy. So when I say James is one of our heroes, whenever we have the really, really challenging things that we need to be doing, which is what this Innovating the Industrial World is all about. So, why did you choose to innovate the industrial world, which is what you do?
Well, that was another decision I made when I came out of college is, do I pick a specific industry that I want to be in, such as automotive or something like that, or do I pick kind of like a diversified industrial solutions provider such as what we are, and be able to touch all different types of industries.
Yeah, so what James is talking about, it's really funny because we get a chance to work on things that you literally might see in the grocery store or the drugstore, and how that really affects things, or things that you don't see, things that are might be on an oil rig somewhere, or in the defense industry or whatever, that you literally don't see, but it's incredibly important. So we're going to talk a little bit about some of the really cool things that we've been able to do, that we've helped folks do that we can really relate to, and it's really kind of gets into some of the cool stuff that we get a chance to do. So why don't you tell us a little bit about this printer that we've been talking about?
Yeah, so recently we had one of our customers. They're an OEM that build printing machines, and that's their expertise. They know how to print on various surfaces. One of their primary areas of expertise is being able to print on contoured surfaces, such as like a wine bottle or
bottles and cans,
cups, turvises, that sort of thing. And they had a challenge that they needed help with. Their expertise is being able to move the print heads in a controlled fashion at a very precise precision while the media is spinning, and obviously time all the coloring and everything like that.
Yeah. So think about this for a second. Everybody's seen their printer, their printer at home, maybe a LaserJet or might be an inkjet printer, and you might open the thing and you see the print head moving around like that, moving extremely precisely on a piece of paper that will reproduce a picture. Imagine doing that on bottles and cans and cups that are of various, and they're not all exact, even perfect cylinders, right? So there's some of them are cones, some of them have curves in them. Imagine trying to control those print heads that precisely, but on those types of surfaces
while they're spinning.
Yeah,
and making sure that all the colors are lining up, because you have different print heads with the different colors. So you need to make sure everything's timed and that sort of thing. So yeah, that was this customer's expertise, but their challenge was to provide a high throughput, auto load, auto offload, high volume, precision
quick
printer.
Yeah.
And the design required multiple stations on a rotary fashion. So it was kind of like a rotary indexer where we had this really
Huge.
fairly large table. It was about 6 foot in diameter, and you had
Okay, so when you're opening up the printer, you think about 6 feet, and this thing's big.
Yeah, so imagine this table's 6 foot in diameter, and there's 9 stations, and each one of these stations has a different function. There is a load station, and that's where the bottle or the can or the Tervis gets loaded and starts spinning, and then that station is indexed to the first color print head, where that contoured printing for that color is accomplished, and then it indexes to the next station where the next color and indexes along, and then there's curing, and then there's eventually offload. So it's this big rotary indexer where the print heads, they're moving, but ultimately they're stationary when it comes to where they're located at the station. And we're taking the bottle and we're indexing it 40 degrees.
So we're taking a cup or a bottle and going, wham, moving it. Oh, I shouldn't splash, but moving it, going to this color. And then a lot of people, I think, know that this green, let's say this yellow, this blue, and these colors here are made up of different colors. So you go to 9 different stations, and if you don't stop in the right spot, it's going to look blurry. Exactly. You're going to be able to tell. It's going to have lines in it. It's going to literally be blurry. You're not going to be able to read it if we're not stopping at the right spot.
And so the challenge here was, how do we precisely move these, the bottles or whatever we're printing on? How do we precisely move to each one of these stations in the allotted time? Because the other point of this is that it was a high throughput. This is supposed to have some throughput to have some higher volume of output. And so first we had to determine what did we need, what was required. And that's where, in the printing industry, our customers, the expert, they understood that they needed
so they know about printing, but they don't know about moving it and stopping it and how to build this.
Exactly. They knew what they needed. They knew how precise they needed it to be to not be visible to the naked eye. But they didn't know how to accomplish that. What we were trying to achieve, I guess, was 1,200 DPI, 1,200 dots per inch, which...
Yeah, we can relate to that sometimes because a lot of us as consumers, we're, getting a printer and we want to print a picture of our kids or our cat or whatever. And you can print a picture that you can see and it looks pretty clear at 800 DPI. And we're talking about 1,200, so higher resolution, finer print. And remember, we're talking about over 6 feet.
Right, and if you imagine 1,200 DPI, that's 8/10,000ths of an inch per dot.
Yeah, holy crap. 8. So in the industrial world, if you talk to a number of engineers, you would hear somebody go, "Oh, that was within 8/10." That's kind of not that. Well, it's not tenths of an inch. It's when we say tenth, we mean 10,000th of an inch. So that is 8/10,000th of an inch is what makes up one dot. But as you would say,
but we wanted the precision and accuracy of achieving a quarter dot.
A quarter dot. So 2/10ths of an inch. 2/10ths of an inch is just about 5 microns. Yeah, exactly. So if you do the conversion into metric as 5 microns, what does that mean, John? Well, something we can all relate to is the average human hair is about 50 microns. So you're talking about 1/10 of a hair on a 6-foot table, and we're going to be moving a product 40 degree or 9. We're going to stop 9 times in a circle, and we have to stop it within 1/10 of a human hair every time. Right, and then be able to rotate it and move it within that same precision.
Right, and so that's the beginning. That's the goal.
Yeah, and quick.
Yeah, and it needs to be fast. So the next challenge. Okay, how do you accomplish that? We've got this rotary indexer. Right, we've got a certain rotary precision that we're achieving potentially, and how does that equate to that linear precision that we need out here? Well, that's where you obviously have to do the trigonometry to figure out how precise this angle needs to be at the center of rotation in order to achieve that 5 micron precision out there.
Way out here, 3 feet in diameter, diameter, radius. 6 feet in diameter, 3 foot radius, and you've got to move within that little bit over here. So the amount of the amount of rotational precision is just ridiculous.
Yeah, I think the maximum print radius was about 2.5 feet. So What that equated to, what we were trying to achieve for that quarter dot tolerance, came to 1.4 arc seconds.
Holy crap. Okay.
Now, for someone that doesn't know what an arc second is, there are 60 arc minutes in 1 degree, and there are 60 arc seconds per arc minute. So it's 1/3600th of a degree is
of a
one arc
degree.
second.
Of a 1/3600th of a degree, and then there's 360 degrees in a circle.
Right. So
Holy crap, that's precise.
That's the goal. And that was quite a challenge. What we determined is that there's nothing off the shelf, nothing in the industry, nothing that a manufacturer that was supplying that could provide the power and throughput that we needed, and also achieve that.
How much
level
does this
precision.
thing weigh? This 6-foot table.
So the 6-foot table, fully loaded, would weigh about between 250 and 300 pounds.
Okay, so we're taking 250 or 300 pounds, moving it that precisely. So we can't get up there and go, oh, just a little bit. We have to go bam, 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 quick. And you have this backlash issue, right? So you're talking about if I pick somebody up who's 250 pounds, and I'm not going to tell you how much I weigh, but you try to move me really quickly 40 degrees and stop within that, it's gonna move, right? It's gonna, we call that backlash, but it's a problem.
Well, it's a huge inertia is what this table is going to represent, and any solution that, number one, is going to be able to precisely position is going to need to have no backlash.
Right.
It's going to
zero backlash.
We're going to need to eliminate any type of compliance in the system, and compliance is any type of slop, any type of backlash, any type of torsional windup, any type of lack of stiffness. That's kind of the important property that you need if you want to position a load, get into position, settle into position very quickly and precisely and repeatably. You need a very stiff system. You need a system that has high enough resolution to allow your control algorithms to do their job.
Yeah.
And so it was kind of a combination of what type of control do we need in order to accomplish this, and what kind of mechanics are required that's going to provide the zero backlash, high precision, high stiffness that's needed.
Yeah.
Because it's easy enough. Yeah, I say easy. If you have high enough resolution, if you wanted to move something to that precise and move it slowly, that's fine.
No
there are off-the-shelf solutions that can potentially get there, although not a lot given the precision. But if you want to take that same solution and not move it slow, but move it fast, and index, boom, 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 and get into position to where you're printing without any variation.
Right, because we got it to the naked eye. We got to be able to see it, or it's going to be blurry. Now, I'm going to interrupt you there, but for those of you who are literally in high school or college, and you're like, oh, I don't use math, I don't need to worry about physics. We've already talked about trigonometry. We've already talked about all kinds of momentum calculations and literally force equals mass times acceleration, and
certainly
study and study hard, because as I said before, James is one of our heroes when it comes to this kind of stuff, because these are things that need to be done, and they need to be done in everything that we can relate to, like literally the safety of cars to rockets to like I said, oil rigs to solar, literally all kinds of different industries. These kind of things are really important. What we're describing is something that we can all relate to. Oh, I see something printed on a can or a cup or a bottle. And I'll just draw the distinction that when we're talking about this, there's labels that go on cans and cups and all those kind of things, but that's not this. You can take a label, peel it off, and stick it on a bottle like that. That's a label. That you're going to print flat. But we've got, these folks are trying to, we can save paper, right? Yep. And be able to print directly onto whatever it is. And that's kind of a big deal.
Yeah, I mean, it's...
So study hard.
There's certainly, you think about some of the microbrews that come out. When they first get started, They'll have the standard 16-ounce can, and they'll have a sleeve on it. They'll have their artwork, they'll have their brand on it, but it'll be a sleeve. It'll be paper. Eventually, that can be printed directly to the can. It saves the paper, but then also offers other possibilities, such as, and you'll start seeing this at some of the ballparks. And I had my visual aids, and maybe we'll take a picture of it here and
we'll take a picture and show it to you.
But now we're starting to see these reusable aluminum cans at the ballparks, at ski resorts that have the brand of the team or the resort directly printed on the can. And it's an aluminum can, so it's reusable.
Yeah.
You can wash it, you can reuse it. You don't throw it out, you don't recycle it. It's a reusable can. And because there's no paper on there, it's very easy to wash, clean, and reuse.
That's kind of cool. So again, 250, 300 pounds. This big, enormous thing. I know we had talked a little bit about, okay, how precise do we have to know the position of that thing given the trigonometry? We had talked a little bit about it's literally, I think you mentioned a 30-bit encoder.
Well, that's the next part is we need to be precise to within 1.4 arc minutes. So what does that equate to? There are motors out there, direct drive systems that have a certain resolution of encoder. A 20-bit encoder, for instance, is about 1 million pulses per rev, which sound quite a bit.
That's crazy, yeah. Think about that. So one revolution, we know 1 billion different points.
Well, a million.
Okay, sorry.
20-bit is 1 million.
Okay.
And there were some solutions out there that are 20-bit encoders. That's not good enough for this application.
Mm-hmm.
1 million encoder would get each pulse would be more than an arc second.
Okay.
And we need 1.4 arc seconds. So that was not going to achieve what we needed to achieve. So we looked at a 30-bit encoder,
okay,
which is 1 billion pulses per rev. And with that 30-bit encoder and the 1.4 arc seconds that we were trying to achieve, I think our positioning window was within 1,000 pulses. So out of the billion pulses, that 30-bit encoder, we wanted to position within 1,000 pulses. And that 30-bit encoder allowed us the resolution. We also needed to position within those 1,000 pulses, settle in position, not moving, within a half a second, roughly.
Yeah, because a lot of people, you might not know this either, but when you're moving things like that fast, and this is true whether you're moving things turning it in a circle or, rotating it, or whether or not you're moving in a straight line, that motion, if you show a graph of it over, incredibly, like let's say a high-speed camera or something, it's going to literally look like a wave, where the speed of it is moving this, and then it stops, and then you're going to see, like, literally, if you saw a graph, it's going to be settling out.
A little bit of overshoot, a little bit of settle.
And we've got to make sure that settle is right exactly where you want it. And then when you think about that, it's also true, not just rotating, but in like, oh my gosh, now we start thinking about some of the things that move where safety is an issue and that kind of thing, and we've got to be able to stop them. And know exactly where it is, because then we can make all kinds of good decisions on those things.
Right, and if you have enough time, you can work out the settling. Right, if you could wait a second for it to settle out, then you can have a lot of different solutions that may be able to achieve something. But in order to do the high precision and high throughput, we needed to make sure that we had a very robust control system and very high resolution, but also the mechanics and the motor, they all needed to be properly sized. The mechanics needed to be very high stiffness, because I talked about this before.
Yeah, super duper strong and crazy stiff.
And stiff, because we're going to be generating some very high torques.
Yeah.
Talk about formulas. Torque is inertia times angular acceleration. So we're going to have to accelerate this big inertia at a very high angular acceleration rate. That requires high torque. Power is torque times speed. That high torque and that speed is going to require quite a bit of power out of our system.
To put that in perspective, it's not exactly this much, but just to think about the math, we talked about a 3-foot radius. And so torque, and you're talking about 350 pounds. So if you're moving 350 pounds at 3 feet away from the center, just so you know, 3 times 350. You're at over 1,000 foot-pounds of torque. Just so you know, a diesel engine out of literally a tractor trailer truck or something like that is in the 1,500 foot-pounds of torque. So we're talking about a lot of torque.
Yeah, it's quite a bit. And the other key to precision motion control and servo control and right sizing a system is something we call inertia mismatch.
Okay.
And what I mean by that is that there are motors out there that have the torque and the speed. They've got the power. They've got the torque and the speed to move whatever load you're trying to move. But if that load is really large, if that load has a very large inertia, and you take that inertia and we do calculations to kind of model it as a disc on the shaft of the motor. So we reflect all the different through the different mechanics and the different gears or whatever else. We basically model it as a disc on the shaft of the motor, and then it's the inertia of that shaft versus compared to the inertia of the rotor of the motor. That's what we call the inertia ratio.
Got it.
For most servo control systems, your standard systems, we want to be under 10 to 1 with some of the new algorithms, 20 to 1 between the load inertia and motor inertia. Mm-hmm. If a motor has enough torque and enough power to turn the load, but its inertia is really small and compared to that load, you run into issues with regeneration, but you also run into issues with tuning. It's that settling. It's being able to move that sledgehammer with the head over here. I've got enough torque to move it, but it's going to be hard to stop it. That motor's going to stop itself, and ultimately there's going to be compliance in the system. There's going to be some stiffness or slop in the system, which is going to keep that load inertia from turning, and the motor and the load inertia are going to be kind of out of sync.
So we got to get that right.
So there are some guidelines that we try to stay under with inertia mismatch. For this application, because the settling time was so important, because we didn't have any really time to spare in order to settle out. We wanted to do it as quickly as possible. We needed to properly size the motor and a very rigid, high precision, zero backlash gearbox, along with a high precision rotary ring pinion indexer to get that inertia mismatch to a 1-to-1. So basically we're trying to have that disc be the same inertia ultimately reflected to the motor. That gives us the best chance of minimizing our settling time and getting basically to the next index.
That's awesome. So next time you're walking through the grocery store or the drugstore or whatever, and you see something that's printed on something round, there's a lot of technology in it. A lot. So, and we get kind of excited about that. So that concludes our 11th episode of Innovating the Industrial World. If you like what you've heard, please click subscribe so you know the next time the next episode comes out. If you have any questions or comments, please leave them in the comment section below. We'd love to hear from you. And James, thank you a ton, man.
All right.
Cool.
Pleasure to be here.